Sergo Jindaryani, pronounced right? So the Dr. Sergo Jindaryani is from Fermilab CDF experiments. He was the leader of Silicon Project CDF, and he's the co-convener of high mass Higgs group. And he's going to tell us about searches for Higgs boson.
Can you hear me well? Okay. So you just heard all those great talks by Paul, Vic, Luciana about all this great physics that's been done at the tevatron in the last 25 years. And my job today is actually to tell you about what's considered to be one of the most hot topics of the collider physics this day, and it's the Higgs boson. And especially now with the LHC running, we're really entering the race. So the feeling that I wanted to give you is that exciting time that we had 15 years ago when the top discovery was basically expected is coming back, and we're basically reliving this with the Higgs boson. Now I can say that the quest to find the Higgs actually started more than 20 years ago, and I'll tell you in a minute why I think that it's actually so old. And this quest is actually continuous, and it's an ongoing journey. So we know that the standard model works extremely well, although experimentally there's still one piece that's missing in here. It's a crucial piece, because without that we wouldn't be able to generate in the standard model masses for fermions and the bosons. And so this is why the Higgs boson sort of takes the center stage in the standard model picture. The standard model predicts that the Higgs boson has to be massive, although we don't know what the Higgs mass is. So we have to determine this experimentally. So a little bit of the tevatron trivia. When do you think was the first, let me ask you a question, when do you think was the first Higgs exclusion from the tevatron published? And probably some of you know the answer to this question, but this came up as a surprise to me. So if you go to Spires and if you look for the first tevatron paper that has Higgs in the name, you will find this one from CDF dated 1989, which was published in PRD in 1990, which excluded the Higgs boson between 200 and 1100 MeV. And what's remarkable is that there's still 8 authors on this original paper that are currently doing tevatron Higgs analysis 20 years later. So that's quite a remarkable dedication. So Paul mentioned this in his talk, and I'm not going to go into many details of this, but essentially we learned a lot since that early publication from 1990, and we learned a lot about the Higgs just from the tevatron data by measuring precisely measuring mass of the top and mass of the W. And so as Paul mentioned, precise measurements of mass of the top and mass of the W allow us to set constraints to the mass of the Higgs. We also have the results of the direct searches from lab, and we know from lab that Higgs has to be heavier than 115 GeV. So that essentially sets the scale for the Higgs searches at the tevatron. We know that probing this mass range between 100 and 200 GeV is basically crucial. So why is it so hard to look for the Higgs? To answer this question, I wanted to show you this plot, which basically shows how many Higgs events before any selection requirements are applied, we produce here at the tevatron. And this number depends on the mass of the Higgs, but it ranges somewhere between 30 and 60, depending on the mass of the Higgs. And so, having that in mind, you already know that this has to be an extremely background-dominated analysis, and you will only have a handful of events in the end. That's why it's so important for us to actually have a lot of data, a lot of high-quality data, as much data as possible, and the ability to process this data as quickly as possible. And so we want to say big thanks from both collaborations to all the supporting divisions, which their contribution is essentially critical to the success of the Higgs program. We thank all the Fermilab divisions and also the funding agencies, DOE and NSF. Of course, to get to the Higgs, which, as I mentioned, has really low production rate, really low cross-section, tevatron experiment CDF and D0 had to go long way, essentially, and start from the QCD physics to the heavy flavor physics, top precision measurements of the W mass, hot mass, and of course the story of the last year or two were essentially discoveries of the diboson states and the single top. And you can see that we're reaching pretty high and we're getting close to the Higgs. Now, tevatron searches use Higgs searches use many tools, and I couldn't possibly mention all of them, but I couldn't get away without mentioning one of them, and the reason is that we have really revolutionized the way people look at the multivariate analysis techniques. And one thing that I wanted to mention about this is that we have so few events, so few Higgs events, that we don't want to just look at a certain property of them. We want to explore those events as a whole. And that's what essentially the multivariate techniques allow us to do. They basically allow us to look at all the properties of those events and construct complicated discriminants that explore all those properties and also correlations between them. And so what comes out as an output is essentially a discriminant plot which ranges usually something between -1 and 1, and you can see the backgrounds are typically peak at the low values and the signal peaks at high values of the score. And this region at the high values of the MVA output gives you best sensitivity, essentially drives the sensitivity of the search. Now there's usually one misconception about the MVA techniques. People think that the MVA allows you to solve all the problems and it boosts your sensitivity by a factor of magnitude. And this is not really the case. I mean, we've shown this multiple times, and it's that the simultaneous fit of two most sensitive variables gives only 20% worse result than the MVA technique. But we cannot, of course, just disregard this 20%. I mean, we're fighting really for every percent that we have. So a few words, I'm not going to go into the details of the Higgs production and decay, but it's important to understand how the Higgs searches are done. And so the Higgs is produced through several production mechanisms, and the most dominant is the one where the Higgs is produced alone without any association, and what you get in the end is basically products of the Higgs decay. And there are also other production mechanisms where Higgs is produced in association with a W or a Z boson. Now the decay of a Higgs basically is driven by its mass. If the Higgs mass is low, it decays predominantly into a pair of p quarks, and as Luciano has mentioned in this talk, they give you displaced jets, so you get two jets, two B jets, and if the Higgs is heavy, then it decays predominantly into a pair of W bosons. So this essentially sets the separation between the low mass and the high mass searches of the tevatron. The low mass, in case of the low mass, the decay is BB bar, and this is such a common state of the tevatron, of the PP bar collision, that you couldn't possibly just use the most dominant production mechanism because when the Higgs is produced by itself, because you would be overwhelmed by the background. So you need to use this associated production when decay products of W and Z give you leptons, and so this is additional handle to reduce the amount of backgrounds. In the case of high mass, the situation is completely different. You have two W bosons, and so you could actually get use of, which is a fairly rare state, and so you could get use of this, the most frequent production of the Higgs. I'll just say a few words about the low mass searches and the high mass searches. So there are three dominant modes in the low mass search for the Higgs. There's one common thing in all three of them. You can see I mentioned this already, is that in all three cases, Higgs is produced in association with a vector boson, being W or Z, and in all three cases, Higgs decays into a pair of B jets, two B quarks, and essentially give you B jets in the detector. So essentially, the analysis, the search for the Higgs is really this hunting for dijet resonance. And what you would like to see is something like this, although this picture is actually from the search of the diboson states, where I show you very massive two jets, and you can see jets basically coming from the resonance coming from the vector boson, and you can see with background subtraction, you can see something like this. So something similar you expect to see for the case of the Higgs, but of course it has to be two B jets. We always look at those complicated plots, but it's always nice to see some individual events, sort of like what we call golden events, which are most signal-like events, and so that's what I'm showing you here. This is a